Hello everyone, and thank you for attending my presentation. Today I'll be talking about Bucephalus, a high-level package for solving heterogeneous-agent economic models using deep reinforcement learning in Julia. I will begin by defining terms and explaining the space of problems, then touch on conventional solution methods and their limitations, before presenting the solution method of Bucephalus and its syntax. I will showcase its ability to solve spatial models as well, then close by discussing next steps. A heterogeneous agent economic model typically takes the following form. Time is discrete at infinite horizon. We have a discrete or continuous set of stateful agents who make some choices given their own state Si, aggregate state variable S, such as aggregate productivity, and equilibrium state variables P, such as prices. These choices generate utility, that is, short-term rewards, for the agent as well as determining their future state. Equilibrium variables, such as prices, are determined in terms of an equilibrium condition, dependent on agents' actions. Each period's individual decisions determine next period's individual state, and each period's aggregate decisions determine next period's aggregate state. Bucephalus also supports segmentations of the population, for example into multiple locations or sectors. State variables can be defined at the segment level, such as differing productivities per location or sector. Agents can have multiple relationships to segmentations, so that an agent can live in one location and work at another. Segments can be exogenously assigned, endogenously determined, or chosen by agents under certain assumptions. In reinforcement learning terms, each agent faces a Markov decision process, but certain features of the environment, for example prices, and the evolution of the state space depend on the aggregate behavior of the agents. This setup is motivated by economics, but I believe it should have applications beyond economics, for example, to ecology, and so I have written the package with a minimum of economic-specific vocabulary. When we refer to solving such a model, we generally mean solving for agents' decisions given prices and state, solving for equilibrium prices given aggregate state, and solving for the steady-state equilibrium of the economy, as well as possibly performing simulations or counterfactuals of responses to shocks or changes to aggregate or individual state. These models are conventionally solved using a brute force approach, by discretizing the state space and applying some solution method that relies on computing policy or value functions over the entire state space. When the state space is large, however, these methods are infeasible. This is the so-called cursive dimensionality. Bucephalus solves these models using a reinforcement learning actor-critic approach. More precisely, it allows the user to define their model using a user-friendly model description language, which uses Julia's excellent macro system, then provides a backend which compiles the model and solves it using reinforcement learning techniques. Before 1.0, I plan to incorporate conventional solution methods into Bucephalus as well, replicating the functionality, for example, of the software Dynaire. Multiple classes of agents can be defined, such as households and firms. In this presentation, I will focus on the example where there is only one class of agents. Each class of agents is equipped with a common policy function, taking state to actions, and a common value function, taking state to expected future rewards. The model is defined with a large but finite set of agents. The policy and value functions will each be manifested as a separate neural network. Often, we assume that each agent is too small to internalize the impact of its own actions on aggregate variables, although future versions will allow this internalization. For example, this is necessary for models of monopolistic competition. This is a simple representation of the learning algorithm. We first pick some starting point, and then perform a learning episode, which consists of simulating the model forward t steps. If equilibrium variables are present, we must solve for them by guessing their values, computing actions depending on those values, computing equilibrium conditions, and then updating prices until all equilibrium conditions are equal to 0. After solving for equilibrium, we then draw shocks and update state variables for the following period, and repeat for t periods. After the learning episode is complete, we then update the parameters of the policy and value function networks, whose gradients we have been collecting during the episode. We then select another starting state and perform another learning episode, continuing this process until some criterion is met. For example, that neural network parameters converge. To reduce noise, many learning episodes can be performed, in series or in parallel, before parameters are updated. This is exposed as an option to the user. Before moving on, I would like to discuss the selection of the initial state for each learning episode. As an economist, I am interested in finding the steady-state distribution of an economy. Thus, it makes sense to attempt to draw from the steady state implied by the most recent policy function. For example, we could use the state prevailing at the end of the last episode. Or we could simulate the model forward after updating neural net parameters, but without learning, to draw from the steady state implied from the updated policy function. In cases where path dependence is a concern, we would need to draw fresh new states in addition to the chain method described above. Determining robust techniques for drawing starting states for learning episodes is something that I'm continuing to experiment with, and for which there may be no one-size-fits-all solution. The user will in future be able to configure this themselves. Here's the code for a simple model with a large state space, commonly known as the Crystal-Smith model. Variables of certain kinds are defined as functions of other variables, or as equilibrium or choice variables with some initial value or distribution. Variables are also assigned to agents, segments, or to the model itself in the case of aggregate variables. State var hh.l equals log normal, for example, means that L is a variable individual to each household, and initial values are drawn from a log normal distribution. State dep m.big L brackets L equals mean little l means that the aggregate variable cap L is computed as the mean of the individual little l's. The types of variables, in order of what stage they are computed in each period, are state, equilibrium, which we will see in the next example, choice, and shock. Dep variables are variables that are computed from variables in that stage. State dep variables depend on state variables, for example. Finally, transition defines the rules determining next period's state variables in terms of variables in this period. Here's the code for a simple model in which there are two locations, one with perfectly elastic housing supply and one with perfectly inelastic housing supply. The location with perfectly inelastic housing supply has higher productivity, but this productivity fluctuates over time. Agents rent and cannot save, but can move freely between locations. I would like to note the use of segmentations here. m.lock represents the two locations. One relation or match between agents and locations is defined, called residence. By W residence refers to the vector of wages W in the residence locations of each agent. Each entry in the vector represents one agent, and the value of the entry represents the wage in that agent's residence location. By members L residence refers to the vector of labor endowments L of residence by location. Each entry of this vector is itself a vector representing the L values of each agent whose residence is in the corresponding location. I would like to close with a roadmap of planned features. A high priority is to replace the existing backend, which is patched together from KNet and much of my own code, with a thin wrapper around an existing library. I will also implement alternative solvers, such as the brute force solver, to add functionality and aid in comparing results. The procedure of selecting initial states for each learning episode requires further thought. Solutions should be checked using various methods, such as Euler equation errors, and the option should be added to allow agents to internalize their effect on equilibrium variables in aggregate state. This will significantly enlarge the class of models that Bucephalus can handle, to include a vast class of games with finite players, such as models of monopolistic competition. However, some aspects of the solver may break down in the presence of non-convexities. Finally, I am actively looking for collaborators. Thank you so much for attending. Do contact me if you're interested in this project or if you're just working in a similar area. Thank you everyone so much for your time. Thanks to the tireless organizers, and I hope you have a great JuliaCon 2022.